All right, so for this module, we're going to talk about what's called resolved shear stress. And this is what allows us to think about our slip and our dislocation motion in terms of a shear stress. So the reason we talk about this is because as we kind of have been visualizing in all these edge and screw dislocations is that shear stress is required, right? So we apply a force towards the right of the top part of the crystal, towards the left and the bottom part of the crystal, and the slip occurs in this. However, we've also predominantly been talking about tension, right? And so, excuse me, so if this slip requires shear stress, then we want to kind of figure out how slip can occur in this tensile force mode. And it can do that because we can take a tensile stress, so the force applied to this bar here, in the basically perpendicular to the cross-sectional area, and we can resolve it into stress components normal to and coplanar with any arbitrary plane at an angle from the tensile axis. So basically, if we pick our slip system, we can think about that as a plane at some angle to the tensile direction, and we can resolve stress components in this plane. So let me kind of bring this in another terms. So if we think about the situation here, if you remember from your statics class, the concept of a wedge, right? So we either have the wedge here or wedge here, right? And we can think about those same stresses. So if we apply a stress, for example, something on a wedge, we can think about the forces acting upon that from gravity, and we can resolve them in directions either in the plane of the wedge or perpendicular to that. And the same is true with this. We can think about our tensile sample as basically a wedge because our slip system is going to be at some angle. So that would be kind of the angle of the wedge. And we can resolve the forces in the plane along the slip direction and normal to the slip direction. So that's what essentially what we're trying to do with this. And to do that, we use what's called Schmid's law. This resolves shear stress from a tensile stress. So we take we take a force that's perpendicular or perpendicular to the cross-sectional area, and we resolve that stress in the slip plane and direction. And so that's our slip direction and plane here, the green, and then the red is the cross-sectional area, and the force is applied tensile. And we will look at what happens in the shear stress, so tau r, from the resulting tensile stress. And so what we do is now to get this resolved shear stress, we need the force in that plane, right? So in the plane of the slip plane. And so that's the area of that slip plane divided by the the force, the shear divided by that area. And that gives us the resolved shear stress. And so we can get the relationship between that resolved shear stress and the tensile stress, sigma, based on Schmid's law. And so that's what is down here. So basically, Schmid's law says that the resolved shear stress, so the R in the subscript refers to resolved. So the resolved shear stress is equal to our tensile stress, sigma, multiplied by cosine of the angle here, which is the angle between the normal to the cross-sectional area and the normal to the slip plane. So basically the angle between the planes. And then further multiplied by the cosine of lambda, which is the angle between the force or the tensile force and the shear force. So the directions and the planes. And the important thing to kind of keep in mind here is that since it's sigma multiplied by two cosines of an angle, it doesn't really matter which angle you represent first, right? So as long as you have one or the other. All right. So this resolved shear stress is going to be dependent on orientation, right? The angle between those planes and so forth based on this equation, right? So it will depend on the crystallographic orientation in those cases. So I want to look at a number of scenarios here. So let's say we have a tensile bar and we apply a tensile stress, and then we want to look at the resolved stress, normal, so basically the cross-sectional area. And so we want to look at that plane. So in that plane, lambda equals 90 degrees between those two angles, or sorry, between those two directions. And however, if you plug that in to this expression, you will get a resolved shear stress of 0. So if one of the angles equals 90, then you get a resolved shear stress of 0. So basically, when you have the plane perpendicular to the tensile stress, there is 0 resolved shear stress because of the angle dependency. However, if you now look at 45 degrees, so right in the middle, effectively, so both of those angles are 45 and 45, this gives us a value of the shear stress equal to the tensile stress divided by 2. And so that's what we see here. And then the last situation we want to look at is now a plane that is coplanar to the tensile stress. So in this case, the other angle, so between the planes now, is 90. So what this tells us is if the tensile force is coplanar to the plane that we're talking about, it's also going to have a resolved shear stress of 0. So basically, these two situations, the extremes, have no resolved shear stress. However, at any other angle, you will have some component of shear stress, with the maximum being right in the middle. So the resolved shear stress maximum is when those angles equal 45, and that's when you have a value that is the tensile stress divided by 2. That's our maximum. All right, so this whole discussion is basically getting shear stress from a tensile stress. And so we can get a shear stress at some plane as long as it's not normal to the tensile direction or coplanar to the tensile direction. Other situations, other planes like this one, will have a component of shear stress. Okay, so now we want to look at the situation where slip occurs on one of these planes and slip systems that we talk about. And the condition for slip to occur is when that resolved shear stress that we just talked about surpasses a critical value. And so that critical value is basically tied to the material and the slip system that we're looking at, and it's the amount of force or stress required to move or break bonds within or between the slip planes along a certain slip direction. So basically, this critical resolved shear stress is a material property. So copper in a specific plane and direction will have a specific value at which the bonds will break, and therefore we will have slip. So that's the condition. So the shear stress, the resolved shear stress, has to be greater than the critical resolved shear stress. And those values tend to be on the order of 10 to the minus 4 to 10 to the minus 2 gigapascals of stress. So this allows us to look at a tensile loading of a sample and get resolved shear stress and compare that to a material property, the critical resolved shear stress, to determine when slip will occur or plastic deformation will occur.